you must have seen the lectures for the area velocity relation. Am I right? These relations must have been derived. Okay. Okay, so I'm sure there must be some references given in the lectures. I personally prefer Zucker and Viblar's Gas Dynamics by Zucker and Viblar's. It's very nice. You can refer chapter 5 for these derivations. So I'll just quickly run through the concept here. So I mean, conventionally we know for subsonic flows, the area velocity relation is well taught even in schools. So if the area is decreasing, then the velocity would be increasing. Is that right? We get that from some simple incompressible equations, the continuity equations. For example, rho av is constant or something. This is known. Yeah, so from here we say that, okay, because approximately the density remains constant in the low velocity flows, so if the area is decreasing, the velocity would be increasing. But all this is valid only when we are considering an incompressible flow, right? So we cannot use these equations anymore because we are dealing with compressible flows, and that's why we basically go and derive these equations from the governing equations, and you get this relation where dv by v goes as minus 1 by 1 minus m square into dA by a. So now we can ask how would the velocity change if the area is changing, and you can see that not only is dv by v proportional to dA by a, there is a factor of the Mach number. So there will be a difference when Mach is less than 1 and when Mach is more than 1. So Mach less than 1, which is subsonic flow, if you keep Mach less than 1, you can see that dV by V will be some negative quantity into dA by A, right? Yeah, so if the area is now decreasing, the velocity would be increasing. So what is going to happen in a converging duct? The velocity is going to increase. Okay, but in a diverging duct, the opposite will happen, because now the area is increasing, the velocity will be decreasing. Now this was the case for Mach less than 1. But now if I keep Mach number more than 1, so 1 by 1 minus m square would be a negative quantity, that multiplied with this minus sign. So you will get dV by V goes as some positive quantity multiplied to dA by A. Is that right? Yeah, so for Mach more than 1, in a converging duct, the velocity will decrease. Okay, and in a diverging duct, the velocity will increase. Okay. So similarly, what we can do is we can write the conditions for pressure also. So you can see the pressure equation over here. That goes like this: dP is a function of the Mach number and dA by A, and all the other quantities are anyways always positive, right? Density and velocity square and the gravitational constant. So what is going to happen when Mach is less than 1? dP is directly proportional to dA by A. So if the area is increasing, the pressure is going to increase, right? So here in the diverging duct, the pressure will increase. Yeah, any doubts? Okay, and similarly in the converging duct, we know that pressure is going to decrease. Okay, so this is very intuitive also. But in a supersonic flow, what is going to happen now? So Mach becomes more than 1 in a converging duct, that is when your area is decreasing. So this is a negative quantity. Mach is more than 1, so this is a negative quantity. So pressure will be increasing. So it's opposite of what is in the case of subsonic flow. So in supersonic converging duct, the pressure is going to increase. Okay, and in the diverging duct, pressure is going to decrease. So I hope this is clear. The velocity area relation, pressure area relation is clear, right? Okay, so now can you tell me what is going to happen in a CD nozzle if I start with a subsonic flow? So let us say I start with m less than 1. So what is going to happen? So this is the converging part and this is the diverging part. So this is called a CD nozzle. So what will happen now to the pressure? Yeah, so first the pressure will decrease and then pressure will increase, is it? You are saying that first the pressure will decrease. So why will the pressure decrease? So I started with subsonic flow. Yeah, so in subsonic flow, yeah, pressure will decrease. And then in diverging duct, you are saying pressure will increase. Why? It is not necessary. Oh, okay. So first of all, if you are saying that it will become supersonic, then the pressure should decrease further, right? So okay, so let us clear these concepts first. What is happening is that the flow is accelerating. That is, the Mach number is increasing, right? So we started with a subsonic flow. So what will happen that first the pressure will decrease and the velocity will increase. Now it is possible that at the throat uh, some high velocity was reached but Mach 1 was not achieved. Okay, so if Mach 1 is not achieved, I can say that this pressure simply decreased up till here. Okay, and then after that, because the Mach is still less than 1, say up till here Mach is still less than 1, so then pressure is simply going to increase because it is going to act like a diffuser, right? So what is a diffuser and a nozzle? Before we move on, what is a diffuser and a nozzle? Right, so diffuser is something which decelerates the flow, nozzle is something which accelerates the flow. So in the case of subsonic flow, converging duct is what? Yeah, so converging duct is a nozzle and diverging duct is a diffuser. Okay, and then in the case of a supersonic flow, the converging duct will be, see, velocity is decreasing. Yeah, so it will be a diffuser. And the diverging duct is now going to be a nozzle, right? So that's why we are referring to this as CD nozzle. But see, if Mach 1 is not reached at the throat, if the flow is still in the subsonic regime, then the diverging duct is also going to act like a diffuser. Okay, and the pressure will increase. So this is the case where your flow remains subsonic throughout. Okay, so this is called subsonic regime. Okay, now let us say we reach this critical condition where Mach equal to 1 is reached. Okay, so your pressure keeps decreasing and say Mach 1 is reached at the throat. So there are two possible conditions now. It is possible that Mach just reached 1, but again, the diverging duct acts like a diffuser. So then the pressure is going to increase, and this is the last possible case where the flow remains subsonic throughout the CD nozzle. So this is called subsonic first critical. Okay, this state is called the first critical. And the other option was what, like you said, that the flow becomes supersonic. So now the Mach becomes so here Mach can tend to 1, but it can be less than 1, then the flow will go into the subsonic regime. Or it can happen that Mach tends to 1, but it is slightly more than 1, so then the flow will go into the supersonic regime, isn't it? So then what will happen to the pressure? Yeah, so in the diverging duct also, now the diverging duct is acting like a nozzle because it is going to accelerate the flow and decrease the pressure, right? So this condition is called the third critical. Okay, I will come to what is called second critical, but this is called the third critical, and this is the supersonic flow. Now in this supersonic flow, remember there is no shock sitting anywhere in this CD nozzle, because we started with a subsonic flow, we let it converge isentropically, it reached Mach 1, and then isentropically it again accelerated in the diverging duct. So this particular line that we have plotted is the isentropic supersonic flow in a CD nozzle. But usually what happens is that a shock can sit somewhere in the throat or in the diverging duct, and then let us say it sits somewhere over here. Okay, let's say it is somewhere here. So what will happen up till that point, the pressure was decreasing. So you're aware what happens when a shock comes. Pressure will increase dramatically because shock is going to compress the flow, right? So there will be a shock and there will be a sudden jump in the pressure. So the pressure decreased up to this point, but right after the shock the pressure will increase. Okay, then what will happen? Will it increase like this or will it decrease like this? Why will it increase? No, it is not like a nozzle or something. You basically say that across a normal shock, what happens? Across a normal shock, always the supersonic flow will be converted to a subsonic flow, right? Across a shock, yeah. So the flow after the shock is going to be subsonic. So what will the diverging duct do to a subsonic flow? It will simply increase the pressure, decelerate the flow. Okay, so this is the non-isentropic regime. Non-isentropic because shocks are there. Okay, and when the shock sits exactly at the exit, that is called the second critical. Okay, then there are even more interesting phenomena. So between the first critical and second critical, what can happen? The shock can sit at different positions throughout the nozzle. Then you see what are we actually plotting on the y-axis? Have you noticed we are plotting P exit by P chamber. So there is a chamber ahead of the converging diverging nozzle where the chamber pressure we assume it remains almost constant, and you are allowing the flow to expand into atmosphere where the atmospheric pressure is say P atmospheric, and at the exit we have this exit pressure. So when you are on this blue line, that is the subsonic regime, always you will see that P exit is equal to P atmosphere. Okay, even at the subsonic first critical. And how do we actually ensure that the CD nozzle will whether it is going to operate at the subsonic first critical or at the subsonic supersonic third critical? How do you ensure that? Yeah, so what either you can do is you can change the chamber pressure or you can change the downstream pressure to ensure that this PE by PC ratio is such that it will drive your CD nozzle at the supersonic third critical. So what matters is what is the pressure ratio and what is your downstream pressure, the exit pressure. So now if I keep the exit pressure at this value, then I'll get the third critical. If I keep the exit pressure anywhere between the first critical and second critical, I will get a shock sitting in the CD nozzle. At the second critical also I'll get a shock. What if I keep the pressure value somewhere between the second critical and third critical? What will happen in that case? Or the other question could be, what will happen if I keep the pressure even below the third critical? Then what kind of flows are we going to get? Any idea? very specific condition, the third critical and the first critical, because they are isentropic flows, right? So if I keep the pressure even below the third critical, the flow will remain isentropic, but the exit pressure has not achieved the like you have kept some downstream pressure. Okay, let us say you are controlling some downstream pressure, but your CD nozzle can achieve, by this isentropic flow, it can achieve only this particular exit pressure, and your downstream pressure is lower than the exit pressure, right? Or I can say that the atmospheric pressure into which this flow is expanding, that is much lower than the exit pressure. Then what is going to happen? So you are at a higher pressure at this exit, so you need to expand even further. You need to reduce the pressure even further, right? So you must be knowing of these phenomena called oblique shocks. Do you know what are oblique shocks and expansion fans? Yeah. So these two mechanisms are used. They just occur at the lip of this CD nozzle, and that will control your pressures. So let us consider that you have the CD nozzle now. Let us say you have the CD nozzle, and so we know that the exit pressure is more than the atmospheric pressure. So what do we need to do? What is going to happen? Whether it is going to be oblique shock or expansion fan? Okay, expansion fan. So what happens in an expansion fan is, say for example, the flow is turning around this curve. Okay, so there was a flow coming like this, and it is forced to turn. So it is going to basically go through an expansion fan, and in the process its pressure is going to decrease. Okay, so in that case here, because already this condition is there is an exit pressure which is higher than the atmospheric pressure, automatically expansion fans are going to be created. Okay, so let me just do one thing. For the next diagram, I'll just copy and paste this nozzle here. Okay, so now there will be some expansion fans here. Okay, so let us say that this was PE, and across the expansion fan, say we come to the condition of P1. So in this region now the pressure has decreased. Again it will encounter the other expansion fan, because this expansion fan was coming from the other lip of the CD nozzle. So what will happen now? Further there will be a decrease in pressure, right? So first we wanted to achieve this atmospheric pressure, so P1 became equal to PA, but then it further decreased. So P2 is less than PA. So now what should happen? Because see, for stable conditions we need to ensure that the pressure should be same as the atmospheric pressure, right? So to bring this pressure P2 back to PA, we will need an oblique shock over here. Is this clear? Yeah, so now this will increase the pressure to P3, and we'll say P3 is equal to PA. But again the oblique shock has continued, and that is going to further increase the pressure to P4. So this cycle keeps continuing until and unless your shocks and fans become very weak, and once that happens you cannot really distinguish any expansion fans or oblique shocks in the flow. But in the starting stage you will surely see one expansion fan, then followed by one oblique shock, followed by another expansion fan, and so on. Okay, on the other hand, let us say we had this condition where the exit pressure was less than the atmospheric pressure. So now you have expanded the flow too much, right? So the flow is over expanded. So this condition would be called over expanded. And in the previous case, where your exit pressure was more than atmospheric pressure, you have not expanded it to the atmospheric pressure, so this would be called the under expanded condition. Okay, so now what is going to happen in the over expanded case? Right, correct. So now we are going to have oblique shocks, but because of the same reasons that we discussed. So first what will happen, your exit pressure is going to increase to P1 and that will be equal to PA. But okay, because the shock has continued, what will happen, there will be a P2 pressure which is more than PA. So to decrease it back to PA, we need an expansion fan over here. So this process is going to continue. So this is called an over expanded nozzle. Okay, so these concepts are clear, I hope. Okay, so what I'll do is I'll discuss some sample questions from previous assignments. So I hope the font size is okay. You can see the questions, right? Okay. So question 1, the flow through nozzle is said to be over expanded when the nozzle exit pressure is, so what is the answer? We just discussed it, right? Yeah, less than the ambient pressure. So this is the answer, right? For fluid through a nozzle, what happens to the velocity and pressure? So we are talking about a nozzle. Right. In subsonic? In subsonic or in supersonic or in both? Yeah, in both, because that is the very definition of nozzle. So don't confuse nozzle with converging and diverging duct, right? So what is, we just now, that is why I wrote down very clearly that for subsonic flow the nozzle is the converging duct and diverging duct will act as nozzle for a supersonic flow. But the very definition of nozzle is what? That the velocity has to increase and pressure has to decrease. That is, the flow is going to get accelerated. So any component which is going to accelerate the flow without using any turbo machinery, that is basically a nozzle. Okay, so next question is, select the correct sentence for the fluid flow throughout the duct. So is a converging duct, does it always act as a nozzle for supersonic flow? No. Diverging duct always so just go on, read whether for supersonic flow which one is a nozzle, which one is a diffuser. So for a supersonic flow, is converging duct a nozzle? Yes or no? No. Okay. Diverging duct always acts as a nozzle for subsonic flow. Is this right? No. Okay. And in the case of a supersonic flow, will the diverging duct be diffuser? Okay. So then the last option is, converging duct acts as both nozzle or diffuser, but it depends on the inlet Mach number. Yeah, so this is the correct option. Okay, for a given fluid, the choked mass flow rate of a nozzle can be increased by doing which of the following? So how do you, okay, first of all, what is a choked condition? When Mach number reaches 1, so let us say we had the CD nozzle, and in the CD nozzle at the throat, this is called the throat, right? So here if Mach becomes equal to 1, it is called a choked throat. So yeah, fine, that is Mach 1, but what is choking in that? What is the meaning of choked mass flow rate? So What does it mean that the throat is choked? Say for example, there is some m dot that you are supplying, okay, and you are basically seeing what is the downstream pressure and downstream temperature at the exit and so on. So now if I do any changes at this location, if I change the mass flow rate here, or like basically if you do any changes upstream of the throat, that will not affect the condition downstream of the throat. Are you aware of this concept of choking? Sorry, not? Okay, okay. So this is basically this is the basic funda of choking. Like once the throat gets choked, it's like say you have a pipe and you create a blockage in that. So how much ever, if the blockage is very strong, how much ever water you keep supplying, it is not going to go through the flow, right? Because it is choked. So the literal meaning of the word choked is that whatever changes you do here, it is not going to pass through. So in that sense, the throat gets choked because how much ever mass flow rate you increase here, I mean, ideally you would expect that you are supplying more mass. So here also the mass flow rate should change, the pressure should change, temperature should change, everything, the exit conditions will change. But that will not happen if the throat has reached this condition of mac equal to 1. So this m dot at which choking occurs is called the choked mass flow rate. Now what I want to change is that at what mass flow rate the throat will change. One simple way to do this is basically change the throat area itself. But once you have designed the nozzle and the throat area is fixed, then further how can I change this m dot? So that is the question here. Any idea? Okay, so what you can do is you can change the inlet total pressure, and the other option is you could decrease the inlet total temperature. What is total? The stagnation conditions. Okay, so if you change the if you do any changes in the flow field over here, that is not going to reflect. But remember we said that before the CD nozzle is this huge pressure chamber, and we assume that this pressure chamber's pressure is not going to change, it is like a reservoir or something. So then what is the upstream stagnation pressure? Stagnation pressure upstream is equal to PC, that is chamber pressure. So if I can change the chamber pressure itself, then going back to that graph that we drew, your P by PC will change, isn't it? So when this P by PC changes, yeah, so the exit pressure condition will also change, that at which exit pressure this supersonic third critical is going to be created, or first critical is going to be created. So as a result, the mass flow rate at which choking occurs will also change. And similarly you can change the inlet total temperature, and that will also affect m dot. Okay. Before choking, I'm sorry, what? No, so what I'm trying to say is that could you mute? Yeah, so what I'm saying here is, if m dot if you keep increasing m dot, what will happen here? The if there is choking, then pressure will keep increasing, right? And ideally you would expect that if you are increasing the pressure here, the static pressure is changing, then downstream also pressure should change. That will not happen. If there was no choking condition, you increased m dot, then locally the static pressure will start changing, isn't it? And then that is going to affect your downstream pressure and temperature conditions. But if there is choking and you increase the m dot, it is not going to affect the downstream conditions. That is the process of choking. So that is a phenomena of choking. Okay. Okay, so question 5. Okay, this is just formula based. You can refer any of the books, and I have also given the formula above. So the area MAC relation, can you identify here which option is correct? Is it A? Yeah, right. A is correct. So you can very easily check it also, right? Just put MAC number as more than 1 or less than 1, and check if it is giving you what you expect, because you know that converging duct is a nozzle for subsonic flow, so that also you can check. But then it will get tricky. You should know whether dv by v goes as 1 by m square minus 1, or it is proportional to m square minus 1. So yeah, this is just formula based. Derivations you can refer in the textbooks. Okay, then the next question is, what is the, yeah, is there a question? Okay, so question 6, find out the correct relation between stagnation temperature and static temperature for the isentropic flow through nozzle at sonic condition. So sonic condition means MAC is equal to 1, right? And we know this relation T naught by T is equal to what? Correct. So now you just have to put MAC equal to 1. What will you get? 1 plus gamma minus 1 by 2, and that is nothing but gamma plus 1 by 2, right? So that's your answer. Okay. So the next question is, which one statement is correct about the mass flow rate of air through a choke nozzle? It depends only on the exit pressure and temperature? No, it depends on the inlet conditions. So like that's what we said in this diagram, that it depends on the inlet stagnation pressure and temperature, and it also depends on this PC to PE ratio. But whether choking will occur or not, that you can control from the inlet stagnation pressure and stagnation temperature conditions, right? So option A is incorrect. Then it is maximum for the given downstream conditions. No. So see, it never depends on the downstream condition. So this option is again incorrect by the same logic. It is independent of both inlet and outlet pressure or temperature. No, it depends on the inlet pressure and inlet temperature, right? So it is maximum for the given reservoir temperature and pressure. So this is the correct option. Any questions on this particular concept? Yeah. So always remember that what you can change, see, when choking happens, any changes in the upstream are not going to affect the downstream. Those changes are the changes in the static field. But any changes in the reservoir, that is the stagnation temperature and pressure, that is going to affect your mass flow rate. Okay. Okay, so then next question is, select the correct sentence from the following. For the supersonic inlet through the converging duct, the flow velocity along the length of duct increases or decreases. So yeah, we've seen this. It is just the same question again. So supersonic is MAC more than 1, right? Converging duct, what happens? What happens in converging duct? Yeah, so this is wrong. Okay, then for subsonic inlet, diverging duct. So in a diverging duct, the flow is going to accelerate or decelerate? Decelerate. So if it's a subsonic flow, it will decelerate, the pressure will increase. But here, what have they said? Right, so this seems inlet through the converging duct, the flow velocity along the length of the duct decreases. No, that's not right. Yeah, it increases. Okay, and for supersonic inlet in the diverging duct, we know the flow accelerates, the pressure increases. Okay, this is also correct. Okay, so in the subsonic case, the diverging duct is going to decelerate the flow, and in the supersonic case, the diverging duct is going to accelerate the flow. Oh, sorry, so the pressure is supposed to decrease. Okay, my bad. So the correct answer is option B over here. So you just need to be careful and patient at that time to go through the options correctly. So, okay, for the supersonic flow through the diffuser, the pressure and velocity, whether they increase or decrease. It's the same question repeatedly. Yeah, pressure increases, velocity decreases. Okay, so we'll move on to a different type of question. It's on intakes. So intake is used in any civilian aircraft to do what? So before you see the options, so what is the shape of a intake? What intake are we talking about, by the way? The diffuser. No, I mean it's a diffuser, but you have told its job. So what a diffuser is going to increase the pressure. So you basically answered the question. But it acts as a diffuser. The intake is supposed to be a diffuser. Why? And intake of what? Aircraft engine, right? Yeah. So we have seen in the previous. We've seen in the previous tutorials that you have this intake and it's supposed to be diverging, and there is then a compressor sitting inside, and then it's coupled to a turbine and so on, and then there's a combustion chamber over here. But before the flow goes into all of these turbo machineries, it is going to expand through this diffuser. Right, so what is the purpose of this diffuser? What will it do? Yeah, correct. It will increase the pressure up till the entry of the compressor, and that is in the case where you are in flight and say you are in the cruise condition, right? So in the cruise condition, your flow is coming in and it is going to basically expand like this. Sorry. Yeah, so there is some flow coming in here, and inside it's going to expand. So this is the diverging duct. Now what happens in the case of takeoff? So let us say you are just starting to take off, so velocity was approximately 0. So will it still act like a diffuser, this thing? Yeah, so the intake will then actually try to increase the velocity, and what happens in that case, outside this intake the flow kind of converges in. Okay, so the flow will kind of converge in. So in this portion there will be acceleration. So intake will increase the pressure of air at the entry of compressor, that is correct if we are in the cruise condition. But in the takeoff condition, the job of the intake is to direct the flow into the engine and also accelerate it before it reaches the compressor. Okay, so then I have some more questions. So what is the shape of the nozzle for a civil aircraft, and what is the shape of a nozzle for a fighter aircraft, and why? So for a civil aircraft, what is the Mach number at which you usually fly? Yeah, so it's somewhere between zero point 0.6 to zero point 0.8 typically, and some fighter jets are there which fly at Mach more than 1. Okay, so when you have a subsonic flow, then we will use which type of nozzle? Converging or diverging? Only converging. We will not add a diverging section because the flow is not expected to reach Mach 1, right? Because the exhaust velocity of the aircraft will also never be more than Mach more than 1, right? So we don't need a diverging section. And what happens if you add a diverging section? The flow will start decelerating over here, so that is going to create losses. Okay, so definitely we don't want a diverging section in a civil aircraft. So for a civil aircraft we will have only a converging duct as the nozzle, but for supersonic flows you will have CD nozzles, so that first the converging section will act as the nozzle, and then the diverging section will act as nozzle, because here we expect that Mach would be Mach more than Mach equal to 1 would be reached in the throat. Okay, so I hope this is clear. Okay, so then there's this last question. So what is the optimum length of nozzle for Mach less than 1? Like length as in, I don't want you to tell me length in meters or something, but how would you design the nozzle? So at the end of the nozzle there will be some exit pressure, right? And you'll be flying at some altitude where the atmospheric pressure is say PE. Then what would be the optimum design? So we know what is going to happen for PE less than PA. PE is less than PA. So it is right. It is overexpanded, right? And PE is more than PA. This is underexpanded. So and PE equal to PA is like the optimal expansion. Okay, so which one of these would you like to operate on? Why optimal? Just because it's called optimal expansion? Yeah. No, in overexpanded, underexpanded, there are shocks and expansion fans which are ensuring that subsequently the atmospheric pressure will be achieved, right? So those things will occur. The shocks and the expansion fans will occur. That's not a problem, and they do occur actually. So no. The question here is that why would you like to operate in this condition? You can operate in this condition also, this condition also, that's not a problem, but ideally you would like to operate on this particular condition only. Why? So what happens when there are shocks created? When there is a shock, it is a non-isentropic phenomena, and there is loss, there is energy loss. Okay, there are stagnation pressure losses. So we want to avoid those losses. Efficiency will decrease if there are expansion fans and oblique shocks. Okay, so we don't want these phenomena to occur. So what we usually do is, while designing the aircraft, you can ideally optimize that. See, the aircraft is going to first take off, and then it will cruise for a long time, and then it is going to land, right? So in this cruise condition, it is say approximately going to be at 30,000 feet. Then I can ensure that the aircraft nozzle is designed such that or the engine is designed such that the exhaust pressure would equal the atmospheric pressure at 30,000 feet, which is very different from all the altitudes throughout this takeoff, right? So what will happen at the different altitudes of this takeoff? So here the pressure is much smaller, and you have designed it for this pressure, right? So you have, say, designed it for P30K, P30,000, and that is much lesser than pH at any of these altitudes. So that means your outside pressure will be more than the exit pressure for which you have designed the nozzle. So during takeoff, ideally you would experience this overexpansion. So then what would be the other option? That you can optimize your nozzle at the sea level. And if you optimize at the sea level, as you increase the altitude and the atmospheric pressure is going to decrease, then eventually your aircraft will go into under expanded nozzle. Am I making sense? Yeah, okay. So now the question is that, let us assume you have this jet aircraft and you have optimized the engine such that the nozzle conditions are optimized at sea level. So what happens to the thrust as altitude increases? Thrust will, why will it increase? Okay. Okay, so this is you're saying there is this thrust condition, thrust equation, and in that we have m dot ue minus u inlet plus pe minus pa into a. No, so see, this condition will be if the forces are acting on the nozzle. Okay, so this CD nozzle that you have here, and now you have optimized it at sea level and over expansion occurs, then whatever is this oblique shocks, that is going to create a lot of losses. Do you agree with that? Hello? Yeah, so it is going to create losses, and remember, we are not having a CD nozzle right now, so we are talking only about a turbojet engine which is in a civil aircraft or something. So there is this converging duct only, and then if the exit pressure is not optimal, so then what would you do? Ideally you should have a more converging section, or you should have had a diverging section after this, but you don't have these, so you are not obtaining as much thrust as you can from this aircraft. But as the altitude increases, the thrust is basically going to decrease. Okay, but if you had optimized it at altitude h, then your logic holds, and this term will contribute, it will keep contributing till the altitude is reached, and after that, okay, so it will keep increasing up till here, and then after that it will further decrease. Okay, okay, so this is actually very critical to understand. So think about this more. If you have any doubts, because I'm kind of out of time right now, so if you have any doubts, you can ask me next time. You should think how this thrust is changing with altitude, if the aircraft is optimized at sea level, and if it is optimized at some altitude h, say let us say this is your cruise altitude or something. Okay, okay then. That's all for today. Stop recording.